Alright, so again, as we discussed in class, you are to watch this video and fill out the notes along with it, and then do worksheet 5. So this is just the warm-up that we did in class, just recapping that in order to check that it's a parallelogram, we need opposite sides parallel, meaning same slopes for those. For it to be a rectangle, our intersecting sides need to be perpendicular so that they intersect at a right angle. And then for it to be a rhombus, our diagonals need to be perpendicular. So we had to find new slopes for that. If all those are true, then we know it's also a square since it's both rectangle and rhombus. Alright, so we talked about this information, trapezoids and kites, during a stinger recently. So we're just going to kind of go back through it, recap it, dive in a little bit deeper, and talk about a certain theorem that goes with it. So first off, remember trapezoids and kites, these are not parallelograms. Not parallelograms. They never were, they aren't, and they never will be. Alright? So these are just a specific type of quadrilateral, and it is not a parallelogram. So it does not have those defining properties of parallelogram. Right, a trapezoid is a quadrilateral with exactly one pair of opposite sides parallel, exactly one. So in this picture here, they gave us that BC is parallel to AD, so let's go and draw that in. And for trapezoids in general, you don't necessarily have to have any of your sides being congruent, just that exactly one pair of opposite sides is parallel. Now let's talk about some terminology here. First thing we have are bases. Bases are your parallel sides. So we have BC and AD are bases. So let's write that in. This is a base. This is a base. And as we know, we are all about that base. So then we have BA and CD are legs, which are the non-parallel sides. Alright, so BA and CD are legs. Let's go and write those in. This is a leg. And this is a leg. As we discussed, these cannot be parallel, otherwise it'd be a parallelogram, and it is not a parallelogram. Alright, then our base angles. We actually have two pairs of base angles. A and D are a pair of base angles. Base angles. And then B and C are another pair of base angles. We think of them as pairs because in isosceles trapezoids, they have a particular property. Okay. So then next, let's take a look at an isosceles trapezoid. Trapezoids by themselves don't necessarily have any particular properties that are defining about them other than the fact that there's just one side with opposite sides, or just one set of opposite sides parallel. But an isosceles trapezoid is a specific kind of trapezoid, and this is a trapezoid with congruent legs. Alright, so this should actually have drawn in that this is parallel, so we know trapezoid. And it has congruent legs. So as we see here, PO and RS have, are legs that are congruent. PO and RS, those are congruent legs. Alright, now isosceles trapezoids do have a couple of very particular properties. One is that each pair of base angles is congruent. So remember, our base angles are P and R, so that means that angle P is congruent to angle R. Our other set of base angles is O and S. So angle O is congruent to angle S. These are not congruent to each other, but we have two sets of congruent angles, the base angles. Okay, now our other thing is that diagonals are congruent. So let's go ahead and draw that in. OR. PS. So these diagonals are going to be congruent. PS is congruent to OR. And again, as we discussed, these do not bisect each other because that is a defining characteristic of parallelograms. If they bisect each other, it would be a parallelogram. Trapezoids are not. Alright, there is actually one more thing that kind of is a follow-through, so just make this as a note. For isosceles trapezoids, we have that the different a base angle from one base angle from each set of pairs is actually going to be supplementary. So what I'm saying here is just a note that angle P and angle O are supplementary. Likewise, angle R and angle S are supplementary. And this comes from the fact that we have, again, 360 degrees in a quadrilateral. And let's use a couple of variables here. Let's say that angle P, the measure of it is x. All right, so, and then since R is the same thing as P, that'd be x degrees plus x degrees. And then let's call O and S, those had the same measure, let's just call it y. So if we add all of those up, that would equal 360 degrees. Well, simplifying here, factor out a 2, and then I get x plus y equals 180, which by definition means they are supplementary. So I mean P and O are supplementary and R and S are supplementary. All right, that's just something good to keep in mind. It makes solving some of these problems a lot quicker. So now let's talk about a mid-segment of trapezoid. This is the main thing that I want you to get from this video that we did not discuss in class. Mid-segment of a trapezoid. Pretty straightforward. Just by reading this, you can probably understand it. The mid-segment is the segment that joins the midpoints of its legs. So I'm just going to draw a trapezoid here. Let's make it not quite isosceles. Alright, so the midpoint of each of the legs, the line connecting it, is what we call the mid-segment. Mid-segment. Alright, now with that we have the trapezoid mid-segment theorem. And this is true for any trapezoid. It doesn't have to be isosceles. This is true for any trapezoid. So the mid-segment is always going to be parallel to the bases. And the length of the mid-segment is half the sum of the lengths of the bases. So first let's take a look at parallel to the bases. So our mid-segment is parallel. So here we have our mid-segment is xy. Xy is the mid-segment. Call it mid-seg. Alright? So xy is going to be parallel to dA and CV. That's a defining characteristic. That's the first one here. And then the length of xy, the measure of xy, is going to be half the sum of the lengths of the bases. So we add base dA plus base CV. Add those together and divide by 2, and that's going to give me the length of my mid-segment. You might also see me write it as this, 1/2 times the sum of my mid-segments. dA plus. Same idea there. Right? So those are two things we can take away from it. For any trapezoid, the mid-segment is parallel to the bases, and the length of it is half of the sum of the bases. Alright, so let's take a look at an actual example with this. And there should be some additional information drawn in. I want you to go ahead and show that these two pieces are congruent and these two pieces are congruent. That information should have been drawn in for you. Alright, so this problem asks us to solve for x. We see that, okay, let's go ahead and also show that these are parallel. Alright, so we see this is a trapezoid. We have one set of parallel lines. And we can know that this right here is our mid-segment because this point is clearly the midpoint since these two pieces are congruent. And this is clearly the midpoint since it's bisecting those pieces as well. Alright, so our mid-segment, which is x plus 2, by definition, or by that property, is equal to 1/2 times the sum of our bases. Well, my top base is 4x minus 10. And my bottom base is 8. Okay, so let's solve. You could multiply both sides by 2. I'm just going to go and leave the 1/2 there. So we get 4x plus 2. Distribute that 1/2, we get 2x minus 1. subtract my x, so I get x on the right side, add my 1, so I get 3, and I get x equals 3. This will be my answer for x there. Alright, so that's how we can use mid-segment theorem to help us out with that. Also, I do want to make sure that we are aware that trapezoids, I feel like so often they're drawn with the parallel lines being horizontal. Do know that as long as you just have one set of parallel lines, it is a trapezoid. So even this would be a trapezoid. There's just one set of opposite sides parallel. So sometimes it is turned like that, and I think for maybe it's apt to see that. Okay, so let's take a look at the back side. Okay, so let's take a look at the back side where we talk about kites. Again, we talked about this in Stinger, but let's go through some more, and I'm actually going to show you how we know those other properties to be true. So again, let's take a look at the definition of kites. Reminder, this is not a parallelogram. Alright, a kite is a quadrilateral with 2 pairs of consecutive sides congruent and no opposite sides congruent. We kind of more so focus on the fact that there are 2 pairs of consecutive sides congruent. Alright, so we see here in our picture FG is congruent to FE, and then our other side is GH is congruent to HE. Alright, so we'll see that opposite sides are not congruent, but we do have 2 sets of consecutive sides congruent. Alright, now a defining property theorem is that if a quadrilateral is a kite, then its diagonals are perpendicular. So the diagonals are perpendicular. We talked about in Stinger, the other quadrilateral that has this property is our rhombus, has 2 squares. Their diagonals are also perpendicular. Also, if you remember with the isosceles trapezoid, we said diagonals are congruent. The other quadrilaterals that have that property would be rectangles and squares. Just some side information there. Alright, so if a quadrilateral is a kite, then its diagonals are perpendicular. And again, this is one of those defining properties or theorems. Properties/theorem. And from this, we can actually prove the following. One, that the first thing is that one diagonal bisects the vertex angles. We talked about in class, what I mean by vertex angles is, as you can see, these are 2 isosceles triangles. And because we have sides congruent here. And vertex angles in isosceles trapezoid is the angle formed by those congruent sides. So that's why I referred to it as the vertex angles. But do know that's not the technical term for it. Alright, so one diagonal bisects the vertex angles. So that means we have angle F or GFI is congruent to IFE. And let's go ahead and write it down. Angle GFI is congruent to angle EFI. Okay. And it also bisects the other vertex angle. So we have these down here are congruent. So we have angle GHI is congruent to angle EHI. Okay, so it cuts those angles in half. That's our first thing. Our second thing is that the other diagonal is bisected. So we have that this here is congruent to this here. So let's go and write that in. GI is congruent to IE. Alright, so bisects that diagonal there. And we also talked about in class how we cannot have both diagonals bisected because that would mean it's a parallelogram. So just one of the diagonals is bisected. And you'll notice this is the diagonal that connects the 2 angles formed by the non-congruent sides. Alright, then our last one is actually talking about those angles. Angles formed by the non-congruent sides are congruent. So that means that this angle here, FGH, is congruent to this angle, HEF. So That's our third thing. Let's go and write that in. Angle FGH is congruent to angle FEH. And again, these are the angles formed by the non-congruent sides. Those angles are indeed congruent. Okay, so let's go ahead and break this down. It actually is pretty quick how we can accomplish all these. We're not going to do a formal proof here, but just kind of look at how we can achieve this to be true. So let's break this down. We've got our kite. And we've got F, G, E, H. I'm drawing my diagonals. This is I. Okay, well, what we do have is that we have two pairs of consecutive sides congruent, so we have this information. And then from that first property theorem, we have if the quadrilateral is a kite, then its diagonals are perpendicular. So I'm going to go and draw that. Alright, well, if my diagonals are perpendicular, then that means they're right angles, right? So just keep that in mind. Okay. Well, first, the way to show these are true actually involves our congruent triangles. And you see we've actually got 4 little triangles, and then we can also take a look at these big triangles here, or the top isosceles triangle, the bottom isosceles triangle. So let's actually first take a look at these big triangles here. So to show that those two triangles are congruent, so I'm trying to show that triangle FHG is congruent to FEH. We see we already have 2 chunks of sides that are congruent, so we could use side angle side, we could use side side side. So I'm going to go side 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 because they both share FH, right? So we have FH is congruent to itself, which, as we know, that's the reflexive property. Again, we're just kind of doing a rough sketch here. We're not doing an actual formal proof. Well, if FH is congruent to itself, then now we can state that FHE is congruent to FHG. So with triangle FHE congruent to triangle FHG. So from here we can actually show both 1 and 3. Remember our first property here, this guy, is that one diagonal bisects the vertex angles. Well, now that we just showed that those two triangles are congruent, that means that this little angle is congruent to that little angle. So we then have that angle GFH or GFI, either way you can label it, GFI is congruent to this other little guy, EFI or EFH. Oh look, isn't that part of number 1 here? So we have that, and then also we know these two pieces to be true. All right, so we have GHI is congruent to EHI. And we know this to be true because of CPCTC. So, I'm sorry, we should have written this in here. We know these triangles are congruent by side, side, side. Right after we showed our reflexive property here with this middle line. So now that those two triangles are congruent, we can say those two angles, or those two sets of angles are congruent by CPCTC. And that actually was what our first thing was that we were trying to show. One diagonal bisects the vertex. Now from here we can also state the third property that we have there, which is the angles formed by the non-congruent sides are congruent. So again, we have our congruent triangle, so I can say angle FGH. Here's another thing. Oh, it wasn't there. It was, there we go. Step 3. Okay. FGH, that angle, is congruent to my other one, FEH, this big guy here. Angle FEH. And again, that's my third thing from up here. So just by one set of congruent triangles, I can have all these pieces. This is again all by CPCTC. We have our two triangles, the corresponding parts are also congruent. So then to get that second property, the other diagonals bisected, similar idea, but we're going to use a different set of congruent triangles. I'm going to go ahead and use these guys here. We already have, from the definition, that these sides are congruent, and from that first theorem that a kite has perpendicular bisectors. Well, remember that HL theorem, the hypotenuse leg, these are right triangles, so we can use hypotenuse leg. We have the hypotenuse, the congruent pieces, and then the shared leg here, since it's shared, we know that that's congruent to itself. So again, we're going to use that reflexive property. So we know that Fi is congruent to Fi. It is a reflexive property. And that allows us to state that triangle FIG, big, is congruent to triangle FIE. And we used here the HL, hypotenuse leg. So from there we can now state by CPCTC that GI is congruent to IE. And again, that's what we had up here for the second one. GI is congruent to IE. One of my diagonals is bisected. Alright, so let's go and write that out. So then from here we have that second property that GI is congruent to IE. And again, we know that by CPCTC. So just with two sets of similar triangles, that's how we got those properties there. Again, similar triangles were very helpful. Thank you. Or not similar, congruent triangles. All right, so just to recap, trapezoids, only one set of parallel sides. Isosceles trapezoid is a trapezoid with congruent legs. It has the properties that each pair of base angles is congruent and that the diagonals are congruent. Then we have a trapezoid midsegment theorem, where the midsegment is actually parallel to our bases for any trapezoid, as well as the measure of it is equal to half of the sum of the bases. Then with kites, a more unique quadrilateral, I think. Two sets of consecutive sides are congruent, and with that our diagonals are perpendicular. And so from there we can have the following properties. One diagonal bisects our vertex angle, the other diagonal is bisected, and the other angles are congruent. The angles formed by the non-congruent sides. I feel like that's maybe a little bit harder to keep track of because there's a lot of different stuff there. So again, make sure you definitely review these properties, and doing the homework as well as that worksheet from Stinger will help you kind of nail those down. So just a real quick look. Your homework then, remember, is worksheet 5 after you've filled in these notes. You're going to use those properties to help you solve these. For example, number 1, it says find the measures of the numbered angles in each isosceles trapezoid. They tell us it's isosceles, so we know our base angles are going to be congruent. And remember, the pairs of base angles are the ones along the base. So for number 1 here. Okay. So worksheet 5, let's take a look at that number 1 here. So we have, again, for an isosceles trapezoid, here are my parallel sides, and our base angles would be 96 in this measure of angle 1, and then angle 2 in this other angle here. Those are my base angles, the angles along your bases. All right, well, isosceles trapezoids, we know our base angles are congruent, so I already know then that the measure of angle 1 is 96 degrees. Okay, so to find measure of angle 2 then, well, we know that there's a total of 360 degrees in our quadrilateral, right? And if we subtract the 2 we already know, which would be 96 times 2, which gives me 12, 18, 19. Right, so if we subtract the already known 192 degrees, we have 168 left to divide between the remaining two. Since they're congruent, it has to be divided in half. So 168 divided in half. 2 goes in 6 8 times. 2 goes in 8 4 times. So that gives me the measure of angle 2 is going to be 84 degrees. Okay. Now, we went through all that work, but remember that note that we said on our notes about isosceles trapezoid? For an isosceles trapezoid, I made you write in the note that we have one angle from each set of base angles is actually going to be supplementary. So that's where this is helpful. Instead of having to go through that whole work of finding how many degrees are left and dividing it by 2, what we could just say is, well, once I have that angle 1 is 96 degrees, 1 and 2 would be supplementary. So what is supplementary to 96? 84. 6 and 4 is 0. Okay, well, that's 180 degrees there. So that saves you the time from having to do this work by hand. Right? So knowing that information. So use that to help you out with solving the isosceles trapezoid ones. And then you're going to use your properties to help you out with these kite problems. For example, let's see, number 20, it says find the measures of the numbered angles in each kite. Well, for a kite, we have the angles formed by the non-congruent sides are congruent. So we know that angle 1 is going to be congruent to angle 2. And then it's a quadrilateral, so there's a total of 360 degrees. So 360 degrees, and let's subtract what we already have, so that'd be minus 149 degrees. So 211 divided in half, because these are congruent. So 211 divided in half would be 1. Let's see, goes into it. 105.5 degrees. Whew. So the measure of angle 1 is equal to 105.5 or 1/2 degrees, which is the same for measure of angle 2. So it's just a little bit of arithmetic. Okay? So use that same information and the other properties to help you solve for these variables here. Remember, your homework is worksheet 5, both the front and the back side of it, working with the trapezoids and kites. And then next class, we will review, go over this, and review for your test. Okay. Enjoy your long time without me and your Tuesday off due to voting. Go Buckeyes!